Hi, everyone. For those of you who may not know me, my name is Tarana Solati. I'm the Associate Dean of Research and Innovation in the Faculty of Forestry. And it's my pleasure to welcome all of you to this research seminar. Before we start, I would like to acknowledge that UBC's Point Grey campus is located on the traditional, ancestral, and unceded territory of the Musqueam people. This land has always been a place for learning for the Musqueam people who have passed their traditions, cultures, and history from one generation to the next on this site. We are very grateful to be able to study, learn, and do research on this land. Before I introduce our presenter, I would like to thank Louise for setting up the AV system, Carrie for sending all the emails out, and also Sonia for preparing the posters that you have seen around the building. Now I'm pleased to introduce our presenter, Dr. Minghao Li. Dr. Li is an associate professor in the Department of Wood Science. He's also a licensed professional engineer in BC. Before joining UBC, he was an associate professor in the University of Canterbury in New Zealand. With over 2 decades of research experience in timber structures, Dr. Li's work focuses on developing innovative timber building technology and advancing sustainable construction practices. He was recognized among the world's top 2% scientists by University of Stanford in 2020 and 2024 in his own field. He also serves on several national and international technical committees, including those in engineering, design, and wood, structural, glue-laminated timber, and timber structures. Please join me welcoming Dr. Li.
Thank you, Tarani, for the kind introduction. So it's a great pleasure for me to present some of my favorite topics on seismic design of timber structures. And really, the current challenge is how we're going to build mass timber buildings with improved seismic resilience. And we understand that there's a significant limitations of current seismic design philosophy for building structures. Okay, so with more and more applications of mass timber being built in high seismic regions, it's really raised the concern of us engineers and building owners. Really, the question is how safe we can build buildings with mass timber. Okay, so I will first give you just a brief introduction of the current state of mass timber in Canada. And also, I know most of you guys are not trained as engineers. I will basically touch a bit of basics about earthquakes and buildings. Okay, and then I will share with you some of my research, Ph.D. research project under my supervision in the last few years. Really, the purpose is to improve resilience of mass timber structures in high seismic regions. And then I will wrap up with a brief conclusion. All right, so this is taken from the Canadian government website. It is showing the, it's updating every month. It's showing the current state of the mass timber structures across the country. And so far in Canada, we have a total of 855 mass timber projects, which are being completed under the construction, as well as small portion is already in land. Okay, so this gives us the overview of the picture, right? You notice that more than half of these over 800 mass timber projects actually are located in BC. So we are the leader of mass timber application across the country and also around the world. And the rest mostly are in 2 provinces, Ontario and Quebec. So, and also you notice that among all these mass timber buildings, over 300 projects are institutional buildings. Okay, so which include us UBC as a secondary education institution and also high schools, elementary schools. So the main reason is the mass timber application is also driven by the government, right? In BC, we are familiar with this Wood First initiative, and that eventually really pushed the trend of building more mass timber structures in the public funded domain. And this is a close-up of that map looking at the UBC community, right? We have a total of 19 projects, actually including this particular building, the forestry building, right? We look up the low roof structure here, made out of beautiful parallel PSL products. And also we have the iconic UBC Brockcommon Storewood House, 18-story student housing. So we can see UBC does, right? It's more like a museum of showcasing a collection of mass timber structures. If we walk around on our campus, okay, so you will see quite a few beautiful mass timber buildings. So this particular building, when it was completed in 2017, it actually set the world records of the world's tallest modern timber buildings, okay? Using modern engineered wood products. In this particular building, a lot of glue-lam and CLT have been used. I want to emphasize modern timber building because in Asia, for example, in China and Japan, there are a few historical religious buildings, those pagodas, are taller than this Brockcommons building. This Brockcommons building, total height is about 54 meters. All right. The tallest pagoda in China, which was built over 1,000 years ago, was taller than this. It's about 65 meters tall. Okay. So, but this is really showcased. UBC is really leading in the mass timber application, and we want to build more buildings using mass timber, which is considered as a sustainable construction material compared with concrete and steel. Another new buildings actually currently under construction. I think it's near completion. This is the new Gateway House building on the University Boulevard. Okay, so once it's completed, early next year, it will house the School of Nursing and the School of Kinesiology. Okay. So this building has a total of 25,000 square meter floor area. It's actually similar to our building, Forestry building, including the main building and this corporate area. So total floor area, they're quite similar. And it's a massive building using a lot of glue-lam and CLT. I mentioned UBC is a museum of mass timber buildings, right? So I just picked some of these buildings as an example. Obviously, my favorite building here on the campus, right? The nice atrium in the forestry building, beautiful truss system. These PSL columns supporting the roof system, right? So don't forget, this building was built in 1998, okay? So that really tells us, like, we had a long history of trying to push innovative solutions using mass timber on this particular campus. All right. We also have very strong timber product industry. Okay, so the government website also shows that across the country, we have 19 manufacturing facilities. And the total annual production capacity of this 19 facility for mass timber products is slightly over 1.1 million cubic meters. All right. So just give you some idea about the amount of wood, the engineered wood we can produce. 1.1 million. That's quite a lot. For the 18-story Brockcommons building, the total volume of engineered wood used in that building is slightly over 2,000 cubic meters. All right, so that means we can really build a lot of high-rise buildings with our current production capacity in Canada. All right, so those 19 manufacturing facilities are able to supply high quality mass timber products. And obviously, the most popular ones are currently CLT, cross-laminated timber. This is a game changer for mass timber industry around the world. CLT, cross-laminated timber, originally invented in Europe. And of course, Glued-Lam. Glued-Lam consumes the most significant market share in mass timber industry. So we use a lot of Glued-Lams, and this is not new products. Glued-Lam been invented over 100 years ago. And we can also have, we have also other type of engineered wood products, nail laminated timber. If you go to UBC bookstore, you look up. So the ceiling and the floor system is made out of NLT, nail laminated timber. And if we go to the Orchards Commons, you know, there's a dining hall there, and they also use DLT, Dow laminated timber from Structural Craft for some of the ceiling products. All right, and these are other type of products, LVL, LSL, and PSL. PSL is these, what you see here. Okay, so these are all very high quality and highly value added engineered wood products. So I don't have to go through all these production cycle, all right? So we understand that Glued-Lam is essentially we laminate structural board together along one major direction. So all the wood fibers are oriented along one major direction, and we often use Glued-Lam for frame structures, for beams and columns, all right? For CLT, I would say it's sort of like plywood on steroid, okay? Instead of using thin veneers, we are using dimension lumber, okay? And then laminate them in a crosswise manner, okay? Of course, we needed to apply adhesive on the surface. Most often is on the wider surface, okay? So these type of, obviously, CLT panels, really the size is limited by the transportation and also limited by the CLT press in the plant. So there was early this year, we visited the Kalashnikov, which is one of the major CLT producers in Canada. So their press is able to press 10 feet wide up to 60 feet long CLT panels. It's about 3 meters wide and 18 meters long, up to almost 0.4 meters, so over 1 foot thick. So imagine if you can use, well, these kind of panel size obviously can be used to replace the conventional concrete slabs in buildings, can be used as the floor slabs and the wall panels, etc. Right? So we do have really a strong industry support, okay, to produce these kind of high quality mass timber product in BC. Now I want to touch base a bit on the type of connection systems used to assemble mass timber components to form a building structure. We are mostly relying on these mechanical fasteners together with steel plates to assemble large mass timber components on the construction site. Occasionally, we also use these glued-in rod. It's essentially using adhesive to transfer the mechanical fasteners, the forces between the mechanical fasteners and wood members. All right, but mostly we are using these relatively large diameter fasteners like coach screws, dowels, and bolts, and also these long self-cutting screws. All right. So the dowels and bolts can go up to almost 1 inch in diameter, often used in mass timber construction. And these long self-tapping screws, they are much stronger than the normal wood screw. They're made out of hardened steel. The yield strength can be 3 times higher than the normal structural steel. Okay, so for example, this can go up to 900 megapascal yielding strength. Okay, so they can also come with the different diameters, often from 6 millimeter in diameter to 13 millimeter in diameter. And different lengths, okay, so shorter ones and longer ones up to 1 meter long. Okay, so they offer then really strong connection solutions for us to build mass timber structures because we have to deal with high forces when we build taller and larger mass timber buildings. Fortunately, now we also have these digital manufacturing processing machines. And for example, in the Co-op lab, we have these CNC wood processing station, right? That can be relied on to make very accurate cutting and drilling. Therefore, on the construction site, we will be able to put those mechanical fasteners in very easily in a very accurate manner, right? So this is just showcase some of these manufacturing processing, right? So we can prefabricate some of the joinery for these large members. Imagine in this case, right? We have two knife plates sticking into bigger glue-line members, and then we have to drill all the holes accurately using the digital fabrication equipment. And then on the site, we can get these fasteners into those holes in an accurate manner, right? So these photos taken from a 12-story CLT building built in Quebec City, right? So you look at the size of these knife plates, you know, you have to have very accurate machines to do the work. A lot of people don't think Canada is a seismic country. And we heard a lot, for example, in California, right? A lot of earthquakes there, right? But unfortunately, we are also a seismic country. And particularly, look at the West Coast area. All right. So this map shows the earthquakes, historical earthquakes, in the last almost 400 years. All right. And we do see some scary ones, magnitude of 9. So right here. So this is fairly close to Vancouver, actually. And obviously, somewhere even probably closer to the Vancouver Island. All right. So I'll give you some idea what is the magnitude 9 earthquake looks like. Remember 2011, we had this big Japan earthquake, Tohoku earthquake. I remember the earthquake triggered tsunami and pretty much wiped out large regions in Japan, the coastal area. All right, but based on this map, you know, we need to be really careful about seismicity in the southwestern area of British Columbia. All right, and the recent one, the major earthquake, recent one in Vancouver area actually occurs in 1946. Okay. So during that earthquake, people in Vancouver rushed to the street, a lot of them. So it was some really, from time to time, we needed to be really aware of that. Earthquakes are there, it will happen. We don't have the crystal ball to predict when it will happen, right? But looking at this historical data. So we are aware of this, and that's why in the recent British Columbia Building Code in 2024, we significantly increased the seismic design forces for our building structures. All right, really to try to lower the future risks. So what you see here, with the increase of the seismic design load for typically low-rise buildings, it's a 25% design force increase for low-rise buildings. In the Victoria area, it's even worse. You may see up to 45% increase of the design forces. All right. With this amount of increase of design forces, that actually created a significant challenge for engineers and architects, because you have to put enough strong structural elements to resist the earthquake loads. And that may limit the architectural flexibility of the floor plans, etc. All right, of course, increase the construction cost. The current seismic design philosophy around the world has specified 3 criteria. So for minor earthquakes, we don't want to see buildings having any damage. All right, I remember a couple months ago, we feel a bit of shaking when I was eating lunch in my office, right? So I would say that is a minor earthquake. You feel the shaking, but I remember Greg was looking around, checking any damage or, so it's no damage, right? So what is your conclusion? No damage, right?
I didn't know that until I went and
Oh, you didn't know that? Yeah, probably we are on the level 4, so the taller you feel more, you know. Moderate earthquakes. So moderate earthquakes, we expect some level of damage, but this kind of level of damage should be repairable, okay? So you're not gonna spend a lot of money to repair those kind of damage. For example, on a moderate earthquake, we have the drywall, you may see some cracks, right? It's more like, appearance. And it really doesn't affect any structural performance in future earthquakes. Therefore, it should be repaired. Major earthquakes, large earthquakes. The only criteria for building structures is to protect life safety. Okay? So we don't want to see any casualty of the building occupants in major earthquakes. That often is translated into collapse prevention. All right, if the building collapses, obviously, people get trapped and might be killed as well. So the collapse prevention is the only criteria for building structures under large earthquakes. I'm talking about normal buildings. Of course, you can design more important buildings with much higher seismic performance, right? So ensure, like hospitals, right? You want to still use the hospitals as usual, even under bigger earthquakes. So for normal buildings, life safety is the key. So next I'm going to show you a few slides taken from the Canterbury earthquake occurred in 2011. It's a big one with magnitude of 6.2. And the epicenter of this earthquake is so close to the city center of Christchurch, only 12 meters away. All right, that triggered very strong ground motion. So you look at this light wood frame duplex. Originally, it's a 3-story duplex.
Oh, shit.
Pancaked, so the whole ground level is gone, all right, because of the soft story issue. So what is the performance criteria we mentioned? It's life safety protection, right? So obviously, it's a failure, right? Look at this building. It's the old-fashioned unreinforced masonry building. In Canterbury area, there was still quite of these type of buildings being built by early European settlers, mostly from England. So partially collapsed, obviously, not good, right? Not full collapse, but partially collapse. Look at this side of the structure.
And nobody died.
The iconic Christchurch Cathedral partially collapsed as well, right? Which is no good. This is the worst, okay? This CTV building basically completely collapsed. And this particular building killed over 115 people. Very sad story. All sorts of reasons eventually led to the whole collapse of the structure. Design problem, design deficiency, and also construction quality control. So the post-quake investigation basically identified why this building, this concrete structure collapsed. Total failure. What about, and this is another hotel building in the city center of Christchurch. So it didn't collapse, but the post-quake inspection found there were extensive damage in this building, such as the damage at the end of the concrete beams. We call this plastic hinges. So basically the rebar has been yielded a lot and the concrete layers spalling, etc. All right. So what do you think the performance? Is it? Yes, it's good. But I tell you what, this building is gone. just because it's just too expensive to repair this extensive damage like this. So eventually, with insurance money, they demolished this building and built a new one because it's more expensive to repair this than build a new one. Okay, so what about timber houses? Christchurch area, similar to Vancouver, has a lot of light wood frame residential houses, right? So if you see here like this, and like this, they are okay. All right, but again, very expensive to repair. It's mostly labor cost, right? So COT structures. I mentioned COT was invented in Europe, and this particular building, 7-story building, COT building, was tested on the world's largest shake table in Japan. You see the shaking, yes.
Magnitude of that earthquake.
The magnitude, I think, is the 1995 Kobe. You remember that earthquake killed about 5,000 people in Japan. So magnitude of peak ground acceleration, if I remember correctly, it's about 0.8 G. It's very severe shaking, yes.
What about the Richter scale that we are all here with?
I don't know exact number. It's somewhere in between 6 and 7. It's that the 1995 Kobe earthquake. Right. So no problem. The observers were applauding. Right?
6.9, Craig.
6.9. Thanks, Rob. So we know this is the ground motion. So earthquake will trigger ground motion. And the ground motion creates problems, right? So what's going to affect the intensity of the ground motion? Obviously, the first one is the magnitude, right? We know larger or major earthquakes has more energy released and trigger more ground motion or more intense ground motions. And distance. If the epicenter of the earthquake is so far from the building site, you don't feel anything. And the last one is the local soil conditions. A UBC area, we are sitting on a very good soil condition. Totally different in Richmond. All right. So Richmond areas, Delta area, is very soft soil, very soft sediment there. So we know those ground motions can be amplified in the soft soil. And the worst case, if there's also liquefaction problem, then that's even worse. We have to go back to learn a bit, to just refresh our memory on the high school physics, Newton's second law, all right? Mass times acceleration, it is the inertial forces we design against for buildings. All right, so in this case, 3-story building, we need to calculate the seismic mass of different level and estimate the amount of shaking, the acceleration. Then we can find out the total forces we need to design against. Looking at modern timber buildings, mass timber buildings, we can come up with different systems to resist earthquake load. Mega truss system, braced frame system, moment resisting frame system. Moment resisting frame system meaning we have to connect design beam column joint, very strong and stiff to resist the moment action. And often in COT structures, we see these shear wall systems. We can have platform COT system. We can have the balloon type of COT shear wall systems. I'm going to explain that later. Platform meaning these wall panels are not continuous along the building height. So each level, so on the top of the wall panels, you have the COT floors. So then do this. Okay, so the walls are not continuous. But the balloon type of system is like you build continuous walls, and then your floor panels are attached onto the side of these walls. Okay, the walls are continuous. And then this one is the hybrid system. So UBC block common house using the concrete cores to resist earthquake load and wind load, lateral load. And also we often see people can use steel frame systems. It's a hybrid solution as well. The earth-size building on the main wall use this braced frame system. Okay, I don't know if you are aware of these chevron or K braces. So these are the most critical components in those buildings to resist earthquake, because they form these triangles to stabilize our structure. All right, so these triangles we know is a lot more stable than a square or a rectangle shape. And we use a lot of small fasteners, so the designers want to yield these small fasteners in a big earthquakes, because this yielding of these small fasteners is able to dissipate a lot of energy. Balloon type wall system. This is the photo from the 12-story CLT building in Quebec City, so continuous wall panels. But of course, I mentioned there's a limitation for transportation, so you often needed to come up with mechanical connection systems to connect the lower panels with the top panels. Okay. Hybrid structures, concrete cores, we're familiar with this, and BCIT tall timber student housing, recently finished, 12-story, using steel frame structures to resist wind and earthquake loads. It's a hybrid, typical hybrid system, right? So the CLT floor panels, right? They're all majority floor systems built with wood and these braced steel frames resist earthquake. And sometimes we can also see engineers try to introduce these high performance bracing element. These are called BRBs, buckling restraint braces. They are commonly used in high seismic countries like Japan and west coast of the United States in California, mostly in the steel frame structures, because they are able to dissipate a lot of energy under earthquake action. So my previous student, Wen Chen, also did some pioneering work on the BRBs. Okay, so it's a glue-lam frame. We have these BRB bracing elements. So we apply the load on the top of beam to simulate earthquake action, pushing the frame back and forth, and we record the amount of load required to impose that level of displacement. And then we plot the curves between the load and the movement of the top beam. And we can generate so-called these hysteresis loops. If we do seismic research on buildings, you will often see these kind of hysteresis loops, all right? So from these type of hysteresis loops, we will be able to find how strong these structures is, and what is the stiffness, and what is the ductility, what is the total energy dissipation. So the areas enclosed by these loops is essentially the amount of energy absorbed by the system. Okay, often we want to see fat loops, meaning more energy is dissipated. In the last few years, I'm particularly interested in this balloon type of CLT shear walls. One of the main reasons is the current building code still doesn't have enough design information. Okay, so we needed to work on this to help deliver designer solutions. We can have single walls, coupled walls, and beam coupled walls. And again, we want to use self-tapping screws because they are very easy to use on the construction site. With normal power tool, you can install these screws. You don't have to pre-drill accurately using CNC machines. Most of the time, we use these screws. And this is the large-scale connection testing. We are trying to looking at these particular hold downs, anchoring these walls to the foundation. So these are the hysteresis loops again, right? Again, I said we can dig out a lot of useful information from these hysteresis loops: strength, stiffness, ductility, and energy dissipation. We also looked at repair. I mentioned seismic resilience. We need to figure out how we can quickly repair these damaged connections after major earthquakes. because these connections are the major elements dissipating energy in a major event. We found we can quickly repair these damaged holes, fairly localized, and insert epoxy into the damaged holes and shift the new screws with a certain offset. And we test the connection again. You look at the performance are very similar, very comparable. Okay, it doesn't take a lot of time and effort to repair those kind of damaged systems. And currently, we're also doing some testing in the lab to look at these panel-to-panel connections. And in seismic design, we also want these connections, panel-to-panel connections, to dissipate energy, right? So we done some preliminary testing, and thanks Brandon for cutting these specimens. We do this testing also using screws to connect these panels, and then look at the failure mode. Sometimes we see the fracture failure of the screws with the significant local pressure of the wood. All right, and this is the hysteresis loops we got, and this really provide useful information for us to evaluate how those connections performed under cyclic loading. And last one is to look at beam system. We can use the steel components to link up individual wall panels. By yielding these steel beams, we will be able to even dissipate more energy for these buildings. And we tested a different kind of connection solutions and make sure we're gonna yield these beams without damaged wood. This is fairly challenging, okay? Because these beams can be quite strong. And we have to come up with a strong and stiffer connection solutions. Therefore, we only see the yielding of the beam steel. So in this case, you have to thinking very carefully how to avoid the weakness of the wood. So we do testings for the wall system now, understanding the component behavior, connection behavior. We look at the system behavior. So I'm just quickly showing you the some of these test videos. So this wall actually, if you look at the literacy, it is the strongest COT shear walls ever tested in the lab. Okay, so to my best knowledge, it goes up to 600 kilonewton. Okay, so the maximum base shear forces, which means this wall is able to resist almost 6 tons forces. 20 times stronger than the normal light wood frame walls we used in our residential buildings. 20 times stronger. We also looked at the repair, fixing all these damaged holes, replacing damaged steel beams. We test the wall again using the same loading protocol. It's almost identical loops, right? This demonstrates the repair strategy works pretty well, and we are able to retrofit this wall system after severe damage and major earthquakes. We developed numerical models to look at applications for different height of the buildings, right? Different design geometries for these coupled wall systems. And also we looked at using another type of hold-on technology. Instead of those mixed angle screwed hold-ons, we're using high strength steel tendons to hold the structure down. So the post-tensioning system is very interesting. It's a self-centering system. It's just a rocking mechanism. These are high strength steel. So under earthquake action, they start to rock back and forth, right? And you see that the wall will bring back to its original location, and we can add sacrificial devices to provide additional energy dissipation. So this is a new technology, the low damage seismic design technology, which has been used in a dozen of mass timber buildings around the world, but not one in Canada, all right? So we did this C-shaped post-tension wall testing using high strength tendons, right, to anchor this wall to the foundation. And this is the hysteresis loops of those different wall setups. Right? Again, the strongest over 800 kilonewton. It's a low damage design. Again, we can quickly go back to replace some small components in the middle. And we test it again. So these loops are essentially from the same wall panels by simply change some of the connection details and replacing some of these devices. The new technology we research has been implemented in real projects. So this is a 6-story CLT structure built on the South Island of the New Zealand high seismic region, continuous balloon type of wall panels, and using these mixed angle screw hold downs, and also these notched shear keys. Okay, so another more interesting project, it comes this one. We researched this C-shape wall system, or sometimes we call this a flanged wall system because we have the 2 flanges, we have the web walls. All right. And we also tested this steel link beam coupled wall system. So what about the combination of these two to form an even stronger system for taller structures? And form a core structure like this for a timber tower. That's what we are currently doing with structural craft, the engineering form, and also microgreen architect. So this is the Ronald McDonald House. It will be built in Vancouver on Willow Street near the BC Children's Hospital. Obviously, the owner is the Ronald McDonald Foundation. But this facility is to provide temporary housing for families where their kids is receiving medical treatment in the hospital. So provide temporary housing for them. So this building actually it's about a $100 million project. Okay, so the Ronald McDonald Foundation is still running fundraising to get cover the whole project budget. The building will use these innovative solutions where my students and I developed for the tall timber towers. The structural craft also received $1.3 million government funding to subsidize the design of the structure because we are not trying to use concrete cores. We are using innovative mass timber wall systems for this particular building. These are additional energy dissipation devices. We use a lot of self-tension screws to attach these devices onto the wall. And these are the post-tension tendons running through the height of the walls, anchor them down to the foundation. And these are the steel link beams, providing coupling effect and also providing energy dissipation for this building. All right, so this is a really exciting project. And once the building is completed, it will be the world's tallest all-timber tower built in high seismic region. Right, so we know in Quebec City, we built that 12-story all-wood solution. But it's not a really high seismic region. A lot of focus for this building is to really think about how we're gonna introduce reliable energy dissipation mechanism. Therefore, we can lower the seismic design forces and make the wood use more economical and more efficient. All right, so I don't have to repeat this information, and we know a lot of things is ongoing in the mass timber research and application, and we are still facing design challenges in designing tall timber buildings, mid-rise or well, mostly high-rise timber buildings in high seismic region. Okay, that's why what you see here, we are using concrete or steel in the timber buildings to resist the wind and earthquake. And because our design code, CSA O86, does not provide enough information for wood solutions to resist earthquake loads. That's why we still need to do research, and we still needed to communicate with industry to come up with appropriate solutions, affordable solutions, etc. And really, I want to thank my previous PhD student, Justin Brown, Wen Chandong, and Ben Morman, Thomas Wright. Four of them are now all working in the industry. They are really experts in the design of mass timber buildings. And also my current student, Killian, is working on this lap joint coupled wall systems. Okay. All right, so that's all my presentation. Sorry, I was running a bit over time.
An excellent presentation, and it showed that you are professional engineers. Any questions?
Great presentation. Thank you so much. A really exciting area of research and scholarship. So congratulations on that. My question is around definitions of mass timber building. And the reason I asked this is just some background. This building was built in 1998. The fire codes precluded us from doing a structurally a wood building.
Yeah.
It was largely because of the lap block.
Yeah.
And you called this a mass timber building.
Yeah.
I would love to say it's a mass timber building when I give tours. But what is a mass timber building? Is it by virtue of the fact that it's structurally out of wood, or that we have large structural members?
Okay, so I would say when we define mass timber buildings, as long as we are using those large cross-section engineered wood products to carry loads, then we can define.
Beams are carrying the load.
They are carrying the roof structural glass roof. Yes. It is a load-bearing components. Therefore, it is a mass timber structure.
Okay, so I can call it a mass timber structure?
Yes.
And I can attribute hybrid you?
Yes. This is also a mass timber structure.
It is.
Yes, it is.
This
Yeah.
is different from that building there.
Yeah.
Large.
Those columns are obviously carry a significant amount of roof load. Imagine if we have a heavy snow event, right?
They call this a master.
Okay.
Yes. Yes.
No, I'm just gonna quote,
Yeah. I got you. Yeah. So it can be even partially part of the structure use mass timber products, and we can call it mass timber structure.
Okay, but then my ultimate question is, is mass timber by virtue of the fact that it's structurally made of wood, or that there's large scale?
I think it's for structural use. Yes, structurally used. Yeah.
So on that, so what about hybrid then?
Yeah, hybrid.
So a mass timber hybrid.
Hybrid.
Very good question. So even though, let's say, people may argue, right, for the tall, the UBC tall wood house, it's a hybrid
It's a
structure.
hybrid.
But what we can argue that particular building use a lot of more wood than concrete. You look at the amount of concrete in that building, the amount of wood used in that building, obviously way more wood used. Often we say, well, it's a really good question. So timber building is not 100% wood. We use a lot of metal pieces. Those are nails and screws, right? And the one I just showed, the steel link beams. It's a combination of different materials. However, we are mainly using wood to carry the load, resist those forces. So then we say, well, this is a timber structure. If we are using mass timber components to resist the forces, and then it's a mass timber structure. Okay, and you look at the 12-story BCIT tall student housing structure, right? And you can still argue, oh yeah, a lot of steel I see, but more wood is used actually in that building.
What would that repair process look like for the large scale CLT walls, especially when there's like local crushing or deformation?
Yeah, it's a really good question. So you notice that we are using these like these screws, right? So the beauty about these screws is we can design these connections to make sure the amount of damage caused by screws is fairly localized. That's what you see in one of the slides. I show all those elongated holes, right? So then we will be able to back up these damaged screws and insert epoxy to fill up those damaged holes. And then just by a little bit offset, we install new screws. And those actually epoxy, once it's hardened, becomes a more like local reinforcement for the screws. That's why you see some cases, you see the damage, the repaired specimen has a bit higher strength than the original pieces, right? So the original specimen. So this is the beauty of using small fasteners. Instead of using those bigger bolts may rupture panels quite a bit, yeah.
So how often do those break? Because I've backed out lots of screws in wood construction and everything snaps once in a while, right? So how much of a problem does that create finishing off the repair?
Yeah, so that's a good question. So it's again about the design approaches we're gonna use. So you see you have these fully threaded and partially threaded screws, right? Imagine if you drive this piece into a solid wood and try to pull this out. Because of this threaded length is fairly long, so you're gonna snap this for sure. But if we have these partially threaded, we can control the amount of threaded part. And then you pull this out, it will come out. Okay, and also we do in our design standard, we do have different design equations to predict possible failure mode, including snapping of these screws. So this is about really engineer's job to control the expected failure mode. Yes.
I have a question. When you were showing the damages after the earthquake
Yes.
or testings, you showed that even the nails, the connections and steel panels were damaged.
Yeah.
How about the wood itself and all those wood panels, beams? How about those?
So the
damages.
yeah, so as I just mentioned, we want to confine the damage in the local connection area. For example, near these fasteners. So the main structural panels for the bigger members, they shouldn't be damaged. In these,
but will they or they won't actually?
They won't. They shouldn't, because otherwise we have to replace those big members, right? Bigger beams and bigger wall panels, etc. So that make repair probably impossible.
Yeah, thanks for the talk. I'm actually curious about the lifespan of the mass timber building. If you compare to concrete building or hybrid building, so what's the lifespan of the
lifespan? It's the same, regardless of construction material we use. It's 50 years of life service time for regular buildings. So building code doesn't really say, well, a timber building is less. Shorter or concrete steel longer? No, it's the same design, service life, 50 years normally, yeah. Yes.
There was one question because you asked one. Did you ask one?
You can go ahead. Thank you for the presentation. Just a quick question. Can hygroscopic behavior of mass timber or hygroscopic nature affect the performance, seismic performance of the mass timber building?
Sorry, I didn't catch the first part.
Like the moisture uptake,
moisture. Yeah. So obviously we have to keep wood dry. It's something we have to do. Keep wood dry, right? So mass timber, we have to keep it dry, but yes, obviously, if unexpected moisture problem happens, of course, it will affect the performance of the whole structure, affecting durability, affecting normal use, right? People using these buildings may have health issues. What about these? Well, most of the components are not treated, right? And then you may see grow fungi, molds, etc. Right. So this is something we have to avoid by carefully detailing sometimes these connections and well-protected component from the weather. Yeah.
Yeah, more of a comment actually. So you showed in the beginning the concrete building that performed well,
Yes.
but it
Eventually
it's like a
demolished.
tear
Yes,
down.
yes.
How much of, sort of like from a PR perspective, obviously this is a major selling point for mass timber buildings, that the repairability.
Yeah.
Is that actually, like, does that happen, like in terms of pushing this as a major selling point?
I would say at the moment, it might not be the selling point because repairability is something, other materials are also looking at. They can come up with new technology to repair concrete structures quickly or steel structures quickly. But for timber structures, so far, we haven't really built a lot of mass timber buildings around the world. So the amount of seismic experience in mass timber is very, very limited. Okay, I know people have been concrete for over 100 years, right? I would say probably not yeah.
Last question.
At this point, so we've got to the end of the life of the building at 50 or 100 years.
Yes.
Can we easily, you showed pictures where you nicely put them together.
Yes,
Can we take
yes.
them apart that easily
Yeah.
as well?
Yeah, I think so. Yeah, I think so. Because, for example, I mean, there are these kind of connections we researched, right? You can drive screws in with a hand tool. You can also use those power tools to get them out.
Yeah, you're assuming it's the same thing 50 years from now.
Yeah, I understand. Yeah. If the moisture change, maybe you need a higher torque to get them out. But yeah, it is possible. Sometimes we install screw in the wrong position and just back them up. Yeah, it is possible because all these pieces, right? They are all prefabricated, and they ship on site, and then just like putting Lego pieces. And obviously, we can dismantle Lego pieces as well. Yeah.
Great. Thank you very much. Thanks all for coming. Our next seminar will be in January, and that would be for teaching and learning. There is no seminar in December. Thanks a lot.